In the preceding video, you learned how to perform a load analysis and how to model the DC performance of a PV module. In this video, you will learn how to design a grid-connected PV system and calculate its performance. We will discuss how to size a grid-connected PV system, select an appropriate inverter, and determine the various system performance parameters. The concepts discussed in the last two videos will form the basis for this video. In a typical grid-connected PV system, the modules are connected to the grid and to the loads through an inverter. The loads are either powered by the grid or by the PV modules, depending on the conditions during the day. For example, during a period of no sun, the modules will be inactive and the grid will power the loads. When the irradiance is high enough, the grid will act as a bidirectional interface. This makes it possible to both store the energy from the PV modules and supply energy to the loads. For the design of such a grid-connected PV system, we follow an energy balance approach. The goal of this approach is to design a PV system such that the energy consumption and generation are balanced over an entire year. The energy consumption by the loads, as you may recall, is obtained by integrating the instantaneous load power PL. The generated energy density per year is found by integrating the product of the instantaneous irradiance GM and the instantaneous module efficiency eta. The energy generated by the modules is then found by multiplying this number by the total module area, A tot. The total module area is defined as the product of the total number of modules, NT, and the area of a single PV module, A. Now we know the annual load demand and the annual energy generation. To complete the energy balance, we introduce a sizing factor, SF. The system sizing factor is a flexible value that provides a certain degree of freedom to adjust the PV system size during the design phase. It is inserted to allow for additional losses such as the accumulation of dirt on the modules or to increase the system performance. The value of the sizing factor should be greater than 1, and the value of 1.1 is usually assumed as a first approximation. With the energy balance in place, the total number of PV modules required, NT, can be calculated. This number is equal to the product of the load demand and the sizing factor divided by the energy generated by a single PV module. Note that the parentheses in this equation denote the required number of modules is rounded up to the nearest integer that is greater than or equal to the x. For calculating the AC yield of a suitable inverter must be chosen. For the inverter selection, the PV modules are assumed to be operational under the standard test conditions, delivering maximum DC power output. This output is a product of the total number of PV modules and the nominal power output of a single module, which can be found in the module datasheet. The maximum DC power output of the modules should not exceed the maximum allowed DC input of the inverter. The first selection criterion of the inverter is therefore that the output of the PV modules is within the operational range of the inverter. The second inverter criterion considers the nominal DC power of the inverter, PDC0, which should approximately be equal to the PV output power. An additional consideration is whether to use a tri-phase or a single-phase inverter. If the inverter nominal DC power is greater than 5 kW peak, then a three-phase inverter should be used. Otherwise, a single-phase inverter is just sufficient. Based on these criteria, a suitable inverter can be selected from the market or from the inverter database maintained by Sandia National Laboratory. From the selected inverter, we obtain two important parameters for our grid-connected system design: the nominal AC power, PAC0, and the nominal DC voltage, VDC0, of the inverter. With these parameters in mind, we can decide how to configure the modules in the PV system. The total number of modules is equal to the product of the number of series connected modules in a string and the number of such strings connected in parallel. The number of series connected modules, NS, is calculated by dividing the nominal DC voltage of the inverter by the averaged maximum power point voltage of the PV modules. You learned how to calculate this averaged MPP voltage in the previous video. Note that the NS value is obtained by rounding down the calculated value to its nearest integer. But why is this value rounded down instead of rounded up? To understand that, let's quickly go back to the instantaneous VMPP calculations discussed in the previous video. This figure shows the variation of VMPP over time for a single PV module. This instantaneous VMPP multiplied by the numbers of modules connected in series gives the instantaneous VMPP for the entire string. For the PV system to perform effectively, the instantaneous PV string voltage should be within the inverter's operational voltage range at all times. This is indicated by the shown condition. By rearranging the terms, the voltage limits of an inverter for a single PV module are related to VMPP and the number of series connected modules according to shown equation. Now, if you round up the value of NS, a fraction of the peak voltages in the shown VMPPT curves gets cut off. This consequently leads to a small voltage loss and a loss in the output power. In order to minimize this loss, the number of series connected modules gets rounded down to the nearest integer. We have now chosen an inverter and determined how many modules should be series connected in a string. In the next video, we shall continue our discussion of grid-connected PV system design by determining the number of parallel connected strings.